In the last class, we showed one way to analyze recursive algorithms. You will recall that solving an algorithmic problem involves 3 steps. 1. Design. 2. Correctness. And 3. Analysis. By analysis, we mean the running time of the algorithm and the memory requirement of the algorithm. An algorithm takes time to run to completion. In the same way, an algorithm also requires memory to run to completion. How long the algorithm takes to finish execution, how much memory the algorithm requires to complete the execution. These two are the measures of the efficiency of the algorithm, the performance of the algorithm, how good the algorithm is, how efficient the algorithm is, how well the algorithm performs is measured by these two resources, time and space. Whenever we design and construct an algorithm, we are immediately interested in the running time and the memory requirement, the space requirement of the algorithm. Analysis means we want to calculate the running time and the space requirement without actually measuring, without actually executing the algorithm and measuring the running time and the space required. Do not execute the algorithm in a machine or by a computer without executing. We wish to calculate the running time and the space required. That is the meaning of analysis. And in the last class, for a recursive algorithm, one simple way to analyze the running time is by unrolling the recurrence. That is not the only technique for analyzing the running time of a recursive algorithm. In this class, we will discuss 3 widely used methods for analyzing the running time of the algorithms. They are, one is unrolling, another is recursion trees, and the third method is substitution. We need to be familiar with these 3 methods: unrolling, recursion trees, and substitution. Okay. Whenever we have a recursive algorithm, the first thing that we do is express the running time of the recursive algorithm by means of a recurrence relation. These are examples for recurrence relation. For example, if we denote T of n as the time, the running time of an algorithm which takes an input of size n. Suppose in the recursive call, the input size is n minus 1. And the algorithm itself does a constant amount of work. Then we say T of n is equal to T of n minus 1 plus 1. This is an example for a recurrence relation. On the left side, we have the definition. On the right side, we have a self-reference. T of n, T is defined but the definition body has T itself as a reference to T itself. Such references are called self-references or recursive references. So this is an example for a recurrence relation. However, this recurrence relation, these are other examples, maybe T of, oh, by the way, when we write a recurrence relation, there will be a recurrence step, there should also be a base case. When the input size is 1, the running time is 1. So every recurrence relation should always have a base case or a bounding case. Another example, suppose T of n is the running time and the input size to the recursive call is n by 2. And suppose the algorithm makes 2 recursive calls, then T of n is equal to 2 times T of n by 2 if n is larger than 1. And maybe when n is equal to 1, it does a constant amount of work 1. And so on. That is, depending upon the algorithm, the algorithm gives rise to a variety of recurrence relations for the running time. However, we should note the recurrence relation in this form does not give us an idea of how long the algorithm will take. T of n is equal to T of n minus 1 plus 1 does not give us an idea whether the running time is constant or linear or quadratic or exponential. Similarly, T of n is equal to 2 times T of n by 2 or T of n is equal to T of square root of n plus 1. In this form, we do not get an idea of how long the algorithm will take to run to completion. This form is called closed form. Oh, sorry, that's the open form. Yesterday also I had the same doubt. We want to solve it, and yesterday we illustrated how we can solve it by unrolling and get something like this is n or n plus 1, something like that. This form is called closed form. From the open form, we do not get an idea of the asymptotic growth of the running time. Whereas from the closed form, we get an idea. T of n is linear. As the input size n increases, the running time also increases linearly. Input size is 10, running time is 10. Input size is 100, running time is 100. Input size is 1000, running time is 1000. So as the input size increases, the running time also increases linearly. Closed form is also called solution. So in this class, what we want to do is how to solve recurrence relations, or from an open form of the recurrence relation, how to obtain a closed form. Why are we interested in the closed form or solution? Because only in the closed form or solution we get an idea of the running time, the asymptotic growth of the running time. Before we proceed further, we want to take a very quick look at the popular asymptotic growths of running times. Common asymptotic growth functions. Okay. N is the input size. As the input size increases 10, 20, 30, 40, 50, 100, 1000, 10,000, 100,000, 1 million, 1 billion and so on, how do the running times behave? These are popular running times, n or n squared or log n or n log n or 2 power n or n factorial. Okay, suppose, okay, how do we measure the running time? We saw that we have to identify a basic operation or key operation of the algorithm and count the frequency, the total number of times that basic operation is repeated. So when we say n, we say the basic operation is repeatedly executed n times. When we say the running time is n log n, then we say the basic operation is repeatedly executed n log n times. When we say the running time is n squared, the basic operation is repeatedly executed n squared times. Suppose execution of the basic operation takes 1 nanosecond. This is equal to 10 power minus 9 seconds. Then for an input size of 10, what is the running time? Suppose this is the algorithm. This is the running, the algorithm has a running time of n squared. If n is equal to 10, what is the running time? Let me write it here. It is n squared, therefore 10 power, okay, 10 into 10, this is equal to 100. The basic operation is executed 100 times. One time it takes 10 power minus 9, one operation. Therefore, this is 10 power minus 9. This is equal to 0.1 times 10 power minus 6. 10 power minus 6 is 1 microsecond. Therefore, this is 0.1 microsecond. Like that, you can calculate. For 20, the running time is 0.4 microsecond. For 30, the running time is 0.9. For 40, 1.6. For 50, 2.5 microsecond and so on. I want to make a very high level overview of a bird's eye view of how these running times behave. Look at this. Suppose the running time is n factorial. If the input size is 10, there are 10 items, it takes 3.63 milliseconds. Even if the input size increases to 20, the running time becomes 77.1 years. Calculate that. So if the running time of an algorithm is factorial, it is practically useless, utterly useless even for very small input sizes. Maybe for 10, it does not matter whether you choose an algorithm of running time n factorial or 2 power n or n squared or n. It is also a very important observation. When the input size is small, it does not really matter how efficient the algorithm is. Suppose we know for sure our input size is always going to be very small, then we should not be wasting our time designing efficient algorithms. Whatever algorithm we can come up with quickly, that should be sufficient. Why? Since the input size is very small, like 10 or a few tens. So a factorial running time algorithm is useless even for small input size as 20. How about this is factorial running time? 2 power n, it is an exponent. Therefore, this is called exponential running time. If an algorithm has a running time 2 power n, where n is the input size, how about this? Up to an input size of 40. Even for an input size of 40, an exponential running time algorithm is useless. 18.3 minutes. Suppose there are 40 vertices in a graph and we want to do some operation on a graph, and the algorithm will take 18 minutes to execute. That algorithm is not useful. From 40 it goes to 50, we are done with, we are finished. 13 days, you had to wait for 13 days for the algorithm to finish, even for an input size of 50. Therefore, we can observe or we can conclude both factorial running time and exponential running time algorithms are practically useless, except for very small size input, very small input sizes such as up to 30 or 40. How about n squared? If the running time of the algorithm is n squared, this is exponential running time. This is factorial running time. And this we call quadratic. N squared. If n cube is cubic and n is called linear. How good is a quadratic running time algorithm? Look here. For an input of size 1 million, it is 16.7 minutes. Not bad. Whereas an exponential algorithm becomes useless even for as small an input of size 40. A quadratic running time algorithm is useful even up to an input of size 1 million. Okay, up to 100,000, it is really useful, 10 seconds. Maybe up to we may say up to 1 million, a quadratic running time algorithm is useful. Beyond that, even that is not useful. So a quadratic time algorithm is not bad. It is practically useful. How about linear time algorithm? Even for an input of size 1 million, it is still only 1 millisecond. Oh, even for 1 billion, not at all bad. So a linear time algorithm is excellent. If the running time increases linearly with the input size, that's an excellent algorithm. Okay. But we are hardly lucky to get a linear running time algorithm for solving a problem. Suppose we get something between linear and quadratic, n log n. Definitely n log n is greater than n. How about that? For 1 million, it is 19 millisecond. For 1 billion, it is 30 seconds. So this is good too. So whenever we have a n log n running time algorithm, still we are lucky. We should give it a name. Some people call that super linear algorithm running time. This one. Super linear. It is not linear, it is more than superlinear. Or because there is a linear term and a logarithmic term, some people give it a nice name, linearithmic. A combination of the two words. Linear and logarithmic. Linear and logarithmic. Okay. Suppose we have a log n times algorithm. Even for 1 billion, it is only 0.03 microseconds. It hardly breaks a sweat. Rarely we have an algorithm with log n running time. So now we have a few popular running times. Log n, this is logarithmic. Linear, superlinear or linearithmic, quadratic, exponential and factorial. Like n squared, we also may have n cubed or maybe even n power 4. All these things in general are called polynomial running time. If an algorithm's running time is polynomial, then we say that the algorithm is practically efficient. Polynomial or better. What is better? N log n is better than polynomial. N is better than polynomial. Log n is better than polynomial. 2 power n exponential is worse than polynomial. Factorial, n factorial is worse than polynomial. So when do you say a problem is solvable algorithmically? If the problem has an algorithm whose running time is polynomial or better, then the problem is solvable. Otherwise, the problem is not solvable, or we say that the problem is intractable. Okay, by the way, we call them asymptotic growth functions. Why is it a growth function? How the running time grows as the input size grows. So instead of running time, we may say they are growth functions. What is asymptotic? How it grows in the limit. When the input size turns to be very large, how does the growth function behave? That's why instead of the just running time, we have this high sounding word asymptotic growth functions, and these are commonly used. One is constant function, log n is logarithmic function, n is linear, n log n is superlinear or linearithmic, n squared quadratic, n cubed cubic, c power n. It need not necessarily be 2 power n, it can be any c power n. You should differentiate between these two. N squared is very good, 2 power n is very bad. Factorial n factorial. And we have ordered these things. 1 is less than or equal to log n, is less than or equal to n, is less than or equal to n log n, less than or equal to n squared, less than or equal to n cubed, less than or equal to c power n, less than or equal to n factorial. This is actually not less than or equal to. Even though I have used a symbol less than or equal to, that means 1 is okay, let me come here. 1 is as fast as or faster than log n. Log n is as fast as or faster than n. N is as fast as or faster than n log n. That is the meaning of the symbol less than or equal to. If the asymptotic growth of the running time of an algorithm is less than or equal less than or equal to the polynomial time, then okay, in general the polynomial can be n power m, where m is a small number. Then the algorithm is practically efficient. If the asymptotic growth of the running time is greater than polynomial time, the algorithm is not practical. Okay, now let us illustrate the 3 widely used techniques for solving recurrence relation. Unrolling is the first technique. We have already seen that. Tower of Hanoi, we have 3 poles A, B, C. We want to transfer. Okay, a tower is a stack of disks with one condition. Smaller disks are always above the larger disks. So suppose we have something like this. This is a disk. This is another disk. This is another disk. This is yet another disk. This is not a tower. Okay. This is a tower. So a tower is an array or stack of disks such that no larger disk is above a smaller disk. And we want to move the tower from pole A to pole B, and we are given a third pole to serve as an auxiliary pole. Suppose there are n disks. How can we do that? Let's assume that we also have a function move disk. We want to move tower A, okay, tower from pole A to pole B. You can use C as an auxiliary disk. We can do it in 3 steps we saw. In step 1, move the top n minus 1 towers, 1 to n minus 1, from A to C, and that is what we do here. Move tower n minus 1 disks from pole A to pole C. You may use pole B as an auxiliary help pole. After we have moved 1 to n minus 1 disks from A to C, that will expose the last disk of size n. Step 2, move that single disk from pole A to pole B. Let us assume that we have a function move disk of size n from pole A to pole B. And then move tower of size n minus 1 from 1 to n minus 1 from C to B. So this is from A to C. This is from C to B. Using A as the auxiliary pole. All right. This is the call. Line 4 is a recursive call. Line 6 is also a recursive call. So one call issues two recursive calls. We have already seen whenever we design a recursive algorithm, we have to ensure two conditions. One, there is a base case. There is at least one base case. And two, the input size to the recursive call is strictly smaller than the input size to the call. What is the input size to the call? N. What are the input sizes to the recursive calls? N minus 1 and N minus 1. So one condition we have ensured. The input size to each recursive call is strictly smaller than the input size to the call. Therefore, the input size will keep on decreasing monotonously, consistently. Eventually, n will become 1 or 0, whatever. We say n is equal to 1 is a base case when there is only, if the tower has only one disk, what should we do? We assume there is a procedure move disk. Using move disk, n is equal to 1 here, therefore move disk n from A to B. Let me ask a few questions. What is the running time of move disk? You need to answer only in terms of constant time, linear time, quadratic time, and so on. Is it constant time or it depends upon the value of n?
So constant thing, sir.
It's a constant thing because it is always size 1, therefore this take constant time c. If the running time of move tower, the call is t of n, the running time of the recursive call at line 4 is t of n minus 1. The running time of the recursive call at 6 is also t of n minus 1. And there is a constant time here. And therefore, t of n is equal to t of n minus 1 plus 1 plus t of n minus 1, which is equal to 2 times t of n minus 1 plus 1 if n is larger than 1. And the base case, if n is equal to 1, t of n is equal to 1. This is the recurrence relation for Tower of Hanoi problem. And we want to solve it. The simplest method for solving a recurrence relation is unrolling. Unroll t of n once. You will get 1 plus 2 of 2 times t of n minus 1. Then unroll t of n minus 1. That would be 1 plus 2 times t of n minus 2. Simplify. 2 times 1 is 2. 2 times 2 is 2 squared. Therefore, this is 1 plus 2 squared times t of n minus 2. Unroll t of n minus 2 once, resulting in 1 plus 2 times t of n minus 3. Simplify. 2 square times 1 is 2 squared. 2 squared plus 2 is 2 cubed. Therefore, you have 1 plus 2 squared plus 2 cubed times t of n minus 3. You can see the pattern. So when this n minus, if there is n minus, for n minus 2, this is 2 squared. For n minus 3, it is 2 cubed. For n minus n or n minus 1, it should be 2 power 1. 2 power n minus 1. So it is 1 plus 2 squared plus 2 cubed and so on. The last term is 2 power n minus 1. The 3 plus n minus 3 should be equal to 0. It should be equal to n. Therefore, n minus 1 plus 1 is equal to n. Therefore, the last term is like this. T of 1, we already know it is 1. This is a geometric series. The formula is the A is the first term and R is the common ratio. A times R power n minus 1. This is R minus 1. Yeah. A is the first term, R is the common ratio, n is the number of terms. So 1 times 1 is the first term, common ratio is 2. 2 multiplied by 2 is 2 squared, 2 squared multiplied by 2 is 2 cubed, and so on. So there are n terms of 2 power n minus 1, and here 2 minus 1. This gives us 2 power n minus 1. As I said, ignore the lower order terms. You get only 2 power n. Therefore, we say that the running time of Tower of Hanoi algorithm is exponential running time. This exponential running time is useful or useless? We have an algorithm, the running time is exponential. Is it a useful algorithm or useless algorithm? What is your understanding from our discussion up till now? You just it's a binary answer, Boolean answer. It is useful algorithm or useless algorithm. If the running time is exponential, big O of 2 power n.
Useless.
Not useless.
Not good,
Useless,
sir.
not good. Oh, you don't want. Oh, he is very afraid of using the word useless. How can you say anything is useless, man? Huh? You should be courteous. You may say it is not good. You should never say something is useless. Who knows? Siru thirumbum palkutta udavum. Huh?
Sir,
Okay. Yeah.
sir, in this particular problem, I guess we are checking all the possible states, sir. So maybe 2 power n might be good, sir.
I am not interested in finding out all possible states. I am only interested in moving the tower from pole A to pole B. Do it in the shortest possible way.
Sir, will be useful only for lower number of disks. Like if it goes really high, then it's gonna be useless.
Oh, this lady has a very positive outlook of life. She does not say it is useless, but she says it is useful for small sized input. Great. What's your name, madam?
Srivarsha, sir.
You see, this is to be commended. Don't say useless. She is actually playing with my own words. I said, except for very small input sizes, exponential and factorial algorithms are utterly, thoroughly useless. And she took it and say it is useful for very small input size. You see, that's an euphemism. When I say it is useful for very small input sizes, there is only another way of saying it is useless.
Yes, sir.
All right. So when we celebrate, oh, we have a Tower of Hanoi algorithm for moving a tower from one pole to another pole, let us not indulge in self-congratulation as though it is a great algorithm. Okay? It is no great algorithm. It's just a play. It's an algorithm. It's a playful algorithm. That's all. There is no great idea behind this algorithm. Okay. So we have illustrated a very famous useless algorithm called Tower of Hanoi, whose running time is exponential. I am not going to do the next two examples. I leave it to you as homework. Power of a number can be expressed as by a recursive function. A power n. A is a number. N is an integer. A non-negative integer exponent. It cannot be a power minus 3, minus 2, and so on. It should be 0 or positive, and it should be integer. We cannot find a power 2.3. If n is equal to 0, a power 0 is equal to 1. Fine, this is easy. What is a recursion step? A power n is equal to a times a power n minus 1. The input size is n here. The input size is n minus 1. Strictly smaller, 1 less than the input size. Therefore, this is a good recursive definition. Translate that into a function. You will get this. What is the running time? T of n is equal to, if this is size n, this is n minus 1. There is no big deal. T of n minus 1 plus 1. Plus 1 is for this. Multiplying the result of power of a n minus 1. There is only one multiplication operation. It takes constant time. So this takes a time t of n minus 1. Multiplication takes one constant time. Therefore, this is 1 plus t of n minus 1. Have we already solved this recurrence relation before? Have you seen this recurrence relation before? Have you
Yes.
seen this for ordered insert?
Yes, sir.
Yes.
You have seen that. Do you remember the running time? If you solve it, what would be T of n? Such questions will be plenty in Cat 1. 1 plus T of n minus 1. 1 plus 1 plus T of n minus 2. 1 plus 1 plus 1 plus T of n minus 3. Can you guess it immediately?
N.
It's going to be n.
N plus 1. So we
Whatever
make
it is. Yeah. It may be n plus 1 or n minus 1. In general, I will say we go of n. Here is the solution by unrolling. A faster recursive algorithm take time to understand this fast power. We will sing and dance about that later on, either in the cat or somewhere. You can write also the recurrence in this way. If n is equal to 0, it is a power 0 is equal to 1. Suppose we want to calculate 2 power 10. One way is 2 times 2 power n. Another nice way is you may say 2 power 10 is equal to 2 power 5 into 2 power 5. And that's what I said here. If n is larger than 0 and even, it is a to the power n by 2 squared. What will happen if it is 2 power 9 or something like that? It would be 2 times 2 power 4 times 2 power 4. So you take n by 2 floor. 9 by 2 floor is equal to 4.5 floor is equal to 4. Square that and then you have to multiply. This most of you will come up with this recurrence relation. If you slightly invert this dividing, halving n and squaring, you will get this. Compare this to this. First half the power, then square. Here, first square, then half. You will get the same. 2 power 10 is equal to 2 squared over 5. Suppose it is 2 power 10. So 2 power 9, it is 2 times 2 squared. You may wonder, what is the big difference between the two? Whether 2 power 5, this is 2 power 5 squared, this is 2 squared to the power 5. Do you really think that it makes any difference? I don't think it makes any difference. By the way, read the literature. This algorithm is due to an Indian mathematician long time back. I forgot the name. I can even rewrite it in one shot. Here, this is a to the power 1. This I may say this is into a to the power 0. So if it is even, it is a to the power 0. It is odd, it is a to the power 1. I can remove the case analysis by saying that this is a to the power n modulus 2. If n is even, n modulus 2 will be 0. If n is odd, n modulus 2 will be 1. So I can combine these two cases into one case. Anyway, that is all these things I leave it to you as homework. Implement a recursive algorithm. That is easy, straightforward translation. Challenging is convert that or from this write an iterative algorithm. If you do that, let me see your algorithm. I will appreciate, I will mark you. Okay. Now here, this is the algorithm. This is size n, t of n. This is t of n by 2. Okay, strictly speaking, t of n by 2 floor. This is also t of n by 2. I am asking a old question. How many recursive calls are made? One call to fast power will result in one recursive call or two recursive calls.
One recursive.
One recursive call,
Yeah.
sir.
Yeah, because it is a if-else statement. Either the if clause will be executed or the else clause will be executed, never both. Therefore, one fast power call, one call to fast power will issue in only one recursive call to fast power, and it is followed by one constant multiplication. Therefore, the running time of the algorithm is 1 plus t of n by 2. I would like you to do the unrolling, but for want of time, I do that and leave some homework. Okay. To solve the recurrence relation, let me assume n is equal to 2 power h, then log n to the base 2 is equal to h. That makes life easier. Let's unroll. T power n will become 1 plus 2 times t of n by 2 squared. Simplify, that is 2 plus t. Then you unroll t of n by 2 squared. That is 1 plus t of n by 2 cubed. Every time the input size has to be halved. So n by 2 squared is halved, it becomes n by 2 cubed. Simplified is 3 plus t of n by 2 to the power 3. You can see the pattern. Eventually it will become h plus, this is 2, this is n by 2 squared. This is 3, it is n by 2 cubed. This is h, this is n by 2 power h. N by 2 power h is simply because n is equal to 2 power h. Therefore, n by 2 power h is 1. T of 1 is a constant, therefore h plus 1. H is equal to log of n. We saw that in the previous slide. Log of n, of course, to the base 2 plus 1. Log 2 to the... Ignore the lower order terms, you get log n. Actually, the base is immaterial. We can simply say log of n. Great. We have seen two algorithms at two ends of the spectrum. At one end, you have an exponential algorithm for tower of Hanoi. At the other extreme, you have a log n algorithm which hardly breaks the sweat even for an input size n of 1 billion. Okay. Most efficient algorithm, running time is log n. Most inefficient algorithm, running time is exponential. By the way, you would have taken note by now, suppose the base is 2, it is still log. Suppose the base is 3, it is still log. The base is 10, it is still log. The base is e, it is still log. The base does not matter. Summation of an array is homework, decimal to binary is a homework. Let's take the time now. All right. We have 15 minutes. We can go with that. The second widely used method for solving recurrence relation is using recursion trees, especially for divide and conquer recurrences. Yesterday we discussed about, not yesterday, the day before yesterday we discussed about merging two sorted lists. I am only repeating this algorithm. We have a linear time algorithm for merging two sorted lists. The recurrence was t of n minus 1 plus 1, and therefore it is big O of n. Okay, or simply I say merging two sorted lists can be done in time n. But that is not the big point. The big point is a merge sort. Algorithm merge sort takes one list as the input and produces another list as the output. Input is a list V, a list of comparable items. The items must be comparable. By comparable, I mean it is possible to apply these operations. Then we say it is comparable. Output is a sorted list containing all the items of V. Base case is if the input list V is an empty list or contains only one item, output is also V. Length of V is equal to 0 or length of V is equal to 1, there is nothing to do, no work to do, therefore return V, constant work, 1. Otherwise, you know by now that there is no need for else is redundant. If you put else, nothing wrong, but even if you don't put else, perfect. Because the control, if the if clause is true, the control will never come here. Length of V by 2. Then we say, take the first half of the list. This means V from start to M. Start to, let's say, M minus 1. And this is M to end. That's a Pythonic idiom. We, instead of writing V from 0 to M, we write V to M. V from M to length of N, we can write like this. Okay. Size is N here. What is the size of this recursive call? Roughly N by 2. Therefore, the running time of the first recursive call is N by 2. This is T of N. What is the size of, what is the input size to the second merge sort? Again, N by 2, T of N by 2. Merge. What is the running time of merge? N. Therefore, this is N plus N plus T of N by 2 plus T of N by 2. That is N plus 2 times T of N by 2. If N is larger than 1, if N is equal to 1, it is equal to 1. This is the recurrence relation for merge sort. In fact, this is an example for divide and conquer algorithms recurrence relationship. Recurrence relation. What is a divide and conquer algorithm? We will discuss about it later in detail. Up till now, we have been deconstructing an instance into only one subinstance and an element. However, it is not mandatory that we have to break an instance into only one subinstance. It is possible and sometimes useful and desirable to break one instance of a problem into two subinstances or three subinstances or four subinstances. Recall when we were given this corner covered board problem, we broke one instance of the board into four subinstances, one board into four subboards. And therefore, it's a very important observation. It is not necessary that an instance of a problem is always divided or broken into one subinstance. It is possible and often useful to break an instance of a problem into more than one subinstance. When we are breaking a problem into more than one subinstance, typically the input sizes to the subinstances are roughly equal. You don't divide that into this is n by 4 and this is 3n by 4. That is not divide and conquer. This is right. So divide and conquer divides an instance into two or more instances, more subinstances. Not only that, the subinstances are roughly equal in size. All right. How do we solve it? We know unrolling. We can use unrolling, but we also want to illustrate the use of another powerful technique called recursion tree. Again, to make life simple, we say n is equal to 2 power h. Take log on both sides. Log n to the base 2 is equal to h. Okay. T of n is equal to n plus 2 times T of n by 2. Unroll it once. It will be n by 2 plus 2 times T of n by 2 squared. If the input is n, then in the recursion it is n by 2. If the input is n by 2, in the recursion it is n by 2 squared. Simplify. 2 times n by 2 is n. 2 times 2 is 2 squared. Therefore, you get n plus 2 squared T of n by 2 squared. Further simplification, 2n plus 2 squared T of n by 2 squared. You may already start seeing the pattern. Let us unroll it once more. Unroll this. N by 2 squared, that is the input size. To the recursion, it is of n by 2 to the power cube. So n by 2 squared plus 2 times T of n by 2 to the power 3. Simplify. 2 squared times n by 2 squared is n. 2 squared and 2 squared get cancelled. 2 squared times 2 is 2 power 3. So you get 2n plus 2 power 3 t of n by 2 to the power 3. Further simplification, 3n plus 2 to the power 3 t of n by 2 to the power 3. Okay, I can immediately jump here. Eventually, when it is 2 power h, this is 2 power h, this is hn. That's what I have written here. nh plus 2 power h plus 2 power h times t of n by 2 power h. Remember, as our assumption was n is a power of 2. Therefore, 2 power h is equal to n. So this is n by n. This is 1. Therefore, t of 1. 2 power h. This is n. h is equal to log n to the base 2. Therefore, n times, replace h by log n to the base 2, replace 2 power h by n, t of 1 by 1, you get n log n plus n. N is a lower order term. N log n is larger than n. Asymptotically, when n tends to become very large, the n will be ignorable compared to n log n. Therefore, the running time of merge sort is big O of n log n, superlinear or linearitmic, whatever. We have time for... Okay, let me just show this and leave some work for you, and we'll continue maybe next week. Okay. A call is given an input of size n by 2. Suppose a contractor is given an input, a work of size n. He gets a subcontractors. I have shown it here. 1, 2, 3 and so on, a subcontractors. He divides the work n into b parts. Therefore, to each subcontractor, he gives a work of size n by b. You will immediately have question, oh, that they should be equal. If there are 5 subcontractors, then the work will be divided equally, n by 5. No, nothing like that. They may be unequal also. There are a subcontractors. The work itself is divided by a factor b. And the contractor, after all, every contractor should do some work also. He divides the work in between a subcontractors. Each subcontractor, he gives a work n by b. The contractor himself does a work equal to f of n, equal to the, it's a function of the work size, work or input, whatever. So the total work done at level 1 is f of n. The next level, every subcontractor does a work of f of n by 2. The work size is n, the work done by the contractor is f of n. If the work size is n by b, then the work done by the contractor is f of n by t. Like this, how many subcontractors are there? A. Therefore, the total work done by subcontractors is level 1 is A times f of n by b. Then each subcontractor, he divides the work by a factor of b. So n by b squared, n by b squared, n by b squared, and so on, and assigns it to a further subcontractors. A subcontractors. So what is the total amount of work done by subcontractors? That this is level 0, this is level 1, this is level 2. Be careful. I number it carefully. Instead of level 1, 2, 3, I number it 0, 1, 2. A times A. Therefore, there is a total of A squared subcontractors. Each subcontractor does an amount of work equal to f of n by b squared, and so on. So in level 3, it will be A to the power 3. Each subcontractor does a work of f of n by b to the power 3. In the last level h, why last level h? Because I have assumed that n is equal to 2 power h, and therefore if it is in each level we are halving the work, n is equal to, sorry, not 2 power h, b power h. In the last level, n by b power h, n by b power h is equal to 1. The work size is just 1 unit. So it is a power h subcontractors at the leaf level. This is at the root level. Each subcontractor does the work f of n by b power h, which is equal to f of 1. Now, instead of the contractor is the first recall. All else are recursive calls. These are recursive calls at level 1. Then recursive calls at level 2, recursive calls at level 3, recursive calls in the last level. Base case recursive calls. What is the total amount of work done by all the calls taken together? F of n plus a times f of n by b plus a squared times f of n by b squared plus a power 3 times f of n by b power 3, and so on. And the last term is a power h times f of n by b to the power h. And that is what we have written here. You can write it as sum of a power I f of n by b power I for I is equal to 0 to h. It is a geometric series. Let me make life a little more easier. Instead of f of n, let me say it is a polynomial n power c. We have a, b, c. Then t of n is equal to f of n plus a times n by c plus a squared time uh, 1 second, sorry. Oh, sorry. I'm wrong. With this we will complete n power c plus a times n by b power c plus a squared times n by b squared power c, and so on. Okay. And this is what you will get. If f of n is a polynomial, t of n is a times this, and this is the simplified thing. What does this mean? It is a, if you simplify that, this is n power c by b power b to the power ic. This n power c is a constant. It does not depend upon I, therefore you can take it out of the summation. And what you get is a divided by b power c by I. This is a geometric series. The common ratio is a by b power c. There are 3 cases. If the common ratio is less than 1, it is a fraction. It is a decreasing geometric series. The first term alone matters. The first term will be the largest term. Most of the work is done at the root by the contractor, by the first call to the function. If the common ratio a by b power c is larger than 1, it is an increasing geometric series. Only the last term matters. Most of the work gets done at the leaves by the base case calls of the function. With this we will stop. Then the other case is a by b power c is equal to 1. So here the largest term, the first term is the largest term. The contractor does most of the work. Here the leaf level subcontractors does most of the work, and here the work is equally divided among all the subcontractors. Nice way to think about. In each of the three cases, what is Tn? T of n here is big theta of, big O of whatever, big O of n power c. What is T of n here? What is T of n here? We will arrive at a theorem which we will call master theorem. We will complete the details next week, but I will upload the slides in LMS. Even before you come to the class next week, you can go through the slide. Okay, we will solve some problems in the in next week classes. That's all. I will stop here.